All right, this is 5.5, the substitution rule. Muy importante, okay? So, if you don't know Spanish, it's very important. All right. You might even watch this a few times, if you don't get it, for sure. It's the most important thing this week. All right. Hold on a second. All right. So, what we're doing is we're going to learn how to evaluate some more difficult integrals, and this is a substitution rule. And this slide is, if you get it, awesome, but I really think you're going to get this with examples. It's one of these things that's way harder to teach, the analytical aspects of it versus just showing you examples. So it'll totally make sense, guaranteed. So, but what you do is you have a kind of a complicated integral that has a function within a function, and you also notice here that its derivative is sitting right beside you. That's kind of one key thing. You should look at the inner function, the one that's inside of another here, composition of functions, that one. And then if you were to take the derivative, you think mentally, if you were to take the derivative, its derivative is actually also part of the integral and is actually sitting right next to it. If that's the case, then there's a much easier way to write the integral, and therefore you can evaluate the integral pretty well with the antiderivatives that we know. So this substitution rule, just kind of the big picture, the substitution rule allows us to integrate more difficult integrals effectively. All right, so here we go. We got our first example, and what you'll do is you'll try to zero in and try to find the function that you think is inside of the other function. So look at the inner function, and you see the 1 plus x squared. So what you'll do is off to the side, you'll let that be the u. So u equals 1 plus x squared. Now you'll notice that if you were to take the derivative of that, it would be 2x, and look, that's sitting right there. It's 2x. So we're going to come over here and we're going to take the derivative. So we would say, du dx equals, and that would be 2x. And then you're typically going to isolate the dx. So because you're going to be making a substitution, hence the substitution rule. So you're going to say du equals 2x dx, and you're going to isolate the dx. So we're going to, actually, let me back up. You're going to try to figure out a way so that you can get the exact same amount over there on the right here as you have right here in the integral. So notice this says 2x dx. This says 2x dx. It's a perfect substitution. So what we're going to do is instead of writing 2x dx, we're going to make the substitution. We're going to replace that with the du. So the 2x and the dx, that's going to be du. And then we're going to have square root. And instead of the 1 plus x squared, we're going to go ahead and put what we know it equals. It equals u. So this becomes our integral that we're going to try to evaluate. So it's a substitution. So now it's a kind of an easy integral. It's a u, u du instead of an x dx. So what we write is, you can change it to a power if it's easier. So we would write u to the 1/2 du. And then we want to add 1 to it and divide, just like we did before. So we're going to add 1, which would be 3/2, and then divide by 3/2. And then, of course, plus your c. And so a little more simplifying, we could put 2/3, and that would be u 3/2 plus c. Now, our problem started off with x's, and so all we have to do is plug the x's back in. So we know that u is supposed to equal 1 plus x squared, so we just go ahead and we plug it back in. So our final answer is 2/3, and we plug the 1 plus x squared back in there, 3/2 plus c, and that is your final answer. Okay? And again, you'll probably get this with a couple more examples. Let me just make sure that's all good. All right, let's try another guy. Okay, as you look at this one, try to identify what the inner function is. Can you tell what the inner function is? Hopefully you can see it's this. So that's what we're going to let u equal. So let u equal whatever the inner function you see, so 4 plus x squared. And then du dx, we're going to find the derivative of that. So that would be, again, this one would be 2x dx. Whoops. I'm getting ahead of myself because when you do a bunch of these, that's what you end up doing because you know you're going to end up multiplying by dx anyways. So we say du equals 2x dx. And come over here and let's start substituting what the integral is. So let's do the 4 plus x squared first, which we know is equal to u. So we're going to say u to the 10th. Now this is a little bit different because we have an x and a dx, and over here we have a 2x dx. So what I like to do is make a perfect substitution. So this side I would have x dx, but I'd have to divide by 2. So if you divide both sides by 2, then on this side it would be du divided by 2. Or that's exactly the same thing as 1/2 du, right? Same thing. So when you come over here to your integral, you replace the x dx with what it equals, which is 1/2 du. So a lot of times what you'll do is you'll put the 1/2 out in front, and then of course you'll put the du right after the other part of the integrand. So that's our integral. We rewrote it with u's so that it would be more simple. So now we're going to evaluate it. So we have 1/2, and we're going to go ahead and just raise the power. So we raise the power, divide by that same power, and then plus c. So final answer would be 1 over 22, depending on how you want to write it, 1 over 22, and then we would go ahead and replace the u. So we would put 4 plus x squared, and then raise it to the 11th, and then plus c. We always have to go back and plug in the x's if our problem started off with x's. So that would be your final answer. Let me check that one out. Just kidding there. So 22, and then plus c. All right. That is it. All right, let's try another guy. Let's try this one. All right, do you see an inner function there? Hopefully you see this inner function. So we're going to let that equal u. So let u equal x to the 4th plus 2. So du dx equals 4x cubed. Du equals 4x cubed dx. So then let's come over here and start trying to rewrite this. So that means we'd have cosine, instead of that, we'd have cosine of u. It's a little more simple. And then here we have x cubed dx. So we come over here and we go, oh, it's not perfect. At least if all the x's are the same, you can make the constants work out. You just would divide by the number like we did before. So x cubed dx, we divide by 4. So that's du divided by 4. We make a perfect substitution. X cubed dx is exactly the same thing as du over 4. So we put the du here, and because that's 1/4, you can just put the 1/4 on the outside just so it doesn't get involved in the whole antiderivative aspect. And now we carry the 1/4, and we find the antiderivative of this, which everybody knows, I'm sure, is sine u, and then plus your c, because we have no limits with all these. And then now we would just replace what we know sine to actually, or what u to actually be. U is actually x to the 4th plus 2. So we'd go ahead and put that back in there, plus c. So that would be your final answer. We've evaluated an integral that would have otherwise been very difficult, or we just wouldn't have any idea what to do. But because of this substitution rule, whenever you have these integrals set up perfectly like this, you can do these ones. All right? Do one more that's indefinite like this. All right. See an inner function, hopefully. See that one there. So let's say that u equals that, and see if it'll work out. So 1 minus 4x squared. And du equals, let's see, that would be minus 8x. Well, see, and then I'm starting to do this, okay? Because you know you're going to be multiplying by dx. So du equals negative 8x dx, just to make it a little quicker. And let's start replacing our integral. So we've got, let's see, on the bottom now, we've got square root of u. And then we've got to replace everything. I want to make that point. Every single part of the integral needs to be replaced, kind of needs to be accounted for. So we have the x dx. So we see we've got x dx, but we've got this extra negative 8. So we're going to go ahead and divide by that. So x dx, perfect substitution, would be du over negative 8, or you could say negative 1/8 du. That's your substitution. So I'm going to put a little negative 1/8 in front, and your du, you know, could be on the top or out to the right, same thing. So I'm going to rewrite this just so that it looks really friendly to evaluate. So that would be u to the, that'd be negative 1/2 du, popping that up and making it a fractional exponent. So that would be negative 1/8, and then I'm going to add 1 to that. So that would be u to the 1/2 divided by half. You know, some people are quicker to, you know, start multiplying by 2, which is great. And then plus c. And now we would, we're dividing by half, so that is the same thing as multiplying by 2. So it probably would have been good if I made this negative 1/4. Hopefully you can see that work there. The 2 would go up there. I'm sure you get that. And then that's u to the 1/2 plus c. And the last thing to do would be to go ahead and plug the u back in there, or plug the what u equals back in there. So that would be negative 1/4, and let's see, that's, it's square root, right, because it's 1/2, so it's 1 minus 4x squared plus c. Final answer. Check that out. Okay. All right. Now, what about if it has limits of integration? How do you do those? Well, that's what I want to show you. All you have to do is one other thing. You just kind of change the limits of integration to be new limits of integration. Other than that, it's not really any harder. Okay. So let's look at this. So we have an inner function. It's 2x plus 1. So let's let u equal that. So let u equal 2x plus 1. The derivative, I'm going to do du, you know, like, because we know we're going to be doing that. So it's actually du equals 2, and then dx. All right, so let's start rewriting our integral. So we have integral, and instead of square root of 2x plus 1, it's actually square root of u. It's a little easier. And then we also have this dx, so we need to substitute that. We have a dx over here on the right, so we're going to divide by 2. So we have du divided by 2. So we make that substitution. We're going to say that dx equals 1/2 du, so we're going to have a du there, and we're going to go ahead and put the 1/2 out in front like we did before. Now, the extra piece is the limits of integration. So the limits are x values. So we start off and we say, okay, x equals. So x equals 0 and x equals 4. And we have to change those so that they're actually u's, so they kind of go with u. So we plug, what we do is we use the equation that establishes the relationship between the two. So we just have to plug in a 0 into this equation to figure out what the u is. So you plug a 0 in there, and it turns out that u equals 1. If you plug a 4 in there, then it would be 2 times 4, so that would be 8 plus 1, so u equals 9. So now we have the new limits of integration. So if we write our integral in terms of u's, then we also have to change the limits. So we go from 1 to 9, and just make sure you put them in the right, oh geez, really? I did 1 to 2. So make sure you put them in the right spots. So 1 to 9. All right, we're ready to roll. We have a brand new integral. So we have 1/2, and remember, you know, this is actually u to the 1/2. I don't really want to take a whole nother step. to evaluate that. So I'm going to go ahead and evaluate it. I'm going to add 1 and divide by that same number. So I'm going to say that that would be u to the 3 halves. It would be divided by 3 halves, but I'm going to go ahead and start doing this, multiplying by 2/3, if that's, that's a little quicker. And I'm going to need to evaluate it from 1 to 9. So there we go. So it looks like we've got 1/3, and if you want, you can keep all this constant stuff on the outside, so it's less busy on the inside. So all the constants you can just leave out of the deal of the whole minus, putting the top one in and then the minus one. So we got 1/3 on the outside. We've got 9 raised to the 3 halves minus 1 raised to the 3 halves, which isn't going to do a darn thing. Okay. And let's simplify. Let's keep going here. So we have 1/3, and then this is the square root of 9. So this is the square root of 9, and then we'd raise that to the 3rd, and then that would be minus 1. So that's 1/3 still on the outside. Square root of 9 is 3. 3 cubed, so that's 27, minus 1. So it looks like we've got 26 times a 3rd, so let's say 26/3. That would be it. That's how you handle it when you have limits. Now, here's the kind of interesting thing. We completely rewrote this integral, and so if you, on your calculator, I'm not going to do this right now, but if you check this out on your calculator, go ahead and graph this function and check out what the integral is from 0 to 4, and then graph this, and of course, the integral will be 26/3. And then if you graph this function, it's a completely different function. It's just a square root function. Go from 1 to 9, and then multiply it by 1/2 and see if you get the same exact area. So it's interesting that you rewrite the integral completely, and all we care about is do we get the same number at the end, and so then it works. All right, uno más. Let me see how I'm doing time-wise. 17. Okay, so I'm all right. So what we do on this last one is same thing. We look for the inner function. So let's let u equal 1 plus 2x, and then du will be 2 dx. And let's try to kind of rewrite this integral. So it looks like it'll be cube root of u squared. And then let's figure out the dx portion. So the dx, we would have to divide by 2. So we do that. And that means we're going to replace the dx with a 1/2 du. So we put that in there. And then we also need to make sure we do the limits of integration. So it starts off with x equals and x equals. So we got x equals 0 to 13. Figure out what the new limits are going to be if we rewrite it in terms of u's. So let's see. Again, we use the relationship that we've established here. And we say if x is 0, plug in a 0 right here. If we plug in a 0 there, then it would be u would be 1. And if we plug in a 13 there, it would be 2 times 13. That would be 26 plus 1 more. So that would be 27. So we got to rewrite this integral with those limits of integration. So it's 1 to 27. Makes sense? Hopefully. So we got 1/2. And let me just kind of off to the side so I don't take up a lot of space. Let me just say that this is the same thing, at least this integral part, is actually u to the, would you agree it would be like negative 2/3? Right, because you pop it up to the top, so it'd be u to the negative 2/3. So that means we would be able to add 1 to that and divide by it. So if we added 1, then that would be adding 3/3. So that would be 1/3. We would divide by 1/3, but that would be the same thing as multiplying by 3. And then we would need to evaluate it from 1 to 27. Okay. Right. So we got 3 halves. And we need to take the 27 and plug it in. So we have 27 raised to the 1/3 minus 1 raised to the 1/3. Keep evaluating there. So we got 3 halves cube root of 27, that's what that is. So cube root of 27, let's say that's 3 minus 1. So final answer, 3 minus 1 is 2. 2's will cancel out, and so we'll get 3. So again, check it out. You can graph the original function and try to find the integral from 0 to 13 on your calculator. And then do the same thing with this brand new looking integral, totally different function. But if you find the area under the curve from 1 to 27, boom, we get the same thing. All right, not bad. 20 minutes of solid examples, okay?